Hi guys, so as the title suggests, this is going to go through the June 2018 Synthesis and Analytical Techniques paper. They're just the multiple choice ones, and I'll carry on making videos on the others as we go through the term, but just go through the multiple choice ones, and I'll go through in detail a bit of these. So it starts with which compound is used as a standard for NMR. And so you look at the examiner's report. I've attached below are all 15 questions in just like a Google Doc, but I've also attached links to the mark scheme, to the actual paper, and to the examiner's report. And you see on this one that most people got this right, that it's A, that it's tetramethylsilane, so SiCH3 4. And this, but a lot of people did put D2O. I think they put D2O because they recognised that D2O is used in NMR. It's used for something slightly different. Tetramethylsilane is used because it produces, all these CH3s are in the same environment, so it produces a singlet. So you get a nice singlet peak. It also, because of the way it's, the structure of it, it's all quite close together, it produces a peak on the extreme right. So nearly everything appears after it. So if we had lots of peaks on our spectrum and then a singlet, we can identify that's our tetramethylsilane, and so therefore that's 0, and everything else we can then set after we've identified where the tetramethylsilane is. So that's why it's a really useful chemical. So number 1 was A. Number 2, which compound is a secondary amide? And for this, we need to know what an amide is. So amide will have the functional group and that's there is actually a secondary amide. A primary amide will have 2 hydrogens attached to the nitrogen. So secondary is where we start to put a carbon in. So put carbon, I might just put R instead. And then a tertiary amide would have this hydrogen replaced by an alkyl chain as well. So the R's in this are just standing for alkyl chains. So we need to identify which ones of these is a secondary amide. And if we go down, number 1, A, is not an amide because we've got a gap between the nitrogen and the carbon. We've got that CH2 alkyl just in between them, so it's not an amide. That's just an amine, although it is a secondary amine. B, same problem again. We've got CH2 in, and also it's an amine, but it's a tertiary amine. We've got a nitrogen with 3 carbons attached. C is our secondary amine. We've got H3C. It's got our carbon with double bonded oxygen, so a carbonyl group. Then it goes to a nitrogen, and that nitrogen's attached to a methyl group and the hydrogen. So it's got those 2 carbon groups, just the 1 hydrogen, so that's our secondary amide. D, because it's attached to 3 carbons, is a tertiary amide. So the answer to that one is C. 3, which of these compounds does not react with nucleophiles? So a nucleophile is something that's going to go for a positive charge. So I'm just going to call my nucleophile X. I'm going to give it a nice lone pair of electrons. So it's there, negatively charged, wants to donate these into a bond, wants to find something to do that with. So I'm just going to draw the functional groups on each compound, just to make this easy. So I'm just going to draw the aldehyde on A. So the aldehyde group on A, because of the carbonyl group, gets a delta plus and delta minus. So because it's got this positive charge, this nucleophile is like, yeah, I'll have some of that, and comes in, and then that breaks off. So that will react with A. So it's not A. Because it had that area of positive charge, or an electron deficient carbon. B has got a double bond. Get my shapes all wrong here. double bond. Oh, that's it. So there's no area of positive. There's no dipole created in this. No delta positive, no delta negative, no positive charge. So this has really got nothing to attract to. In fact, it's going to get repelled by this area of electron density in the double bond. So pretty sure the answer is going to be B, but we can have a look at the others and we can show why it's not the others. So control this quickly. Well, not so quickly, so the case may be. C, so C, then we have a C double O and a CH3. Very quick, so I'm not going to put all the hydrogens in, but here we've got butanone. So because of carbonyl, we can have a delta plus delta minus straight in there. That box. So it is going to react with C for the same reason as A, and then just calling that R rather than drawing all the trains to save my time. D is going to have a delta positive carbon, delta negative chlorine because the chlorine's more an electronegative. So again, straight in here, and off it goes. That's a nucleophilic substitution there. Similar, if this was OH minus, we'll swap that around with the Cl to form an alcohol. So the answer to that one was B, the alkene, because it has no area of positive, no electron deficient carbon or anything like that for the nucleophile to attack. 4, which represents an alicyclic compound. Now you may not have heard this term, alicyclic. It's not often that it comes up, but we've got two types of compounds in organic chemistry. We've got organic and we've got aliphatic. Now, aliphatic, organic are the ones with benzene rings. Aliphatic are the ones that have carbon-hydrogen straight chains. Might have double bonds, but they're essentially carbon-hydrogen chains without benzene rings. And when an aliphatic comes cyclic, so it's both aliphatic and cyclic, we call that alicyclic. So we're looking for a cyclic compound that isn't a benzene ring. So A does have well, no it doesn't, sorry, a benzene ring, we can see there on the left. B, clearly a benzene ring. C, only 2 double bonds in the cyclic compound, so that is not organic, and that looks like it's going to be our alicyclic compound. And D, benzene, so can't be D. So A, B, and D are all aromatic, and C is aliphatic or alicyclic, so it is C. Right, which molecule is not planar? So we need to know bond angles, number of bonds that have been formed there to work out the bond angles. So if we do all 4, we've got our ethene first, C2H6, so 2 carbons at the centre, and then it's going to have 4 bonds in total around each hydrogen. So I think we can already see this one's not planar. We'll have a look at the others. So here we've got around each carbon 3 bonded pairs. One of them's a double bond, but total 3 bonded pairs. So we've got a bond angle of 120 degrees there. Same around this one, 120 degrees around that carbon. It's really pretty much identical. Our hydrogen cyanide, although we've got a triple bond, this is 180 degrees, so we've got a linear compound. Now around each carbon, this time it's got 4 bonds, all pushing equally away. So we get the tetrahedral structure, 109.5, and it is a C2H6. So it's B again for question 5. Question 6, number of peaks on the proton NMR spectrum. We've got our carboxylic compound into a CH2, into a CH with an OH on, into another CH2, into another carboxylic acid. So we've got planar symmetry, first of all. So this hydrogen and this hydrogen, they're going to be identical environments. So we'll call that 1. These two and these two are going to be in the same environment. They're all bonded to exactly the same thing. So that's 2, 3, and 4. So the answer is 4. And that's 6. So that's B for number 6. Seven, work out the atom economies. And this could actually take you quite a while. So I wonder, I have to think they might have phrased this question wrong, and what they wanted was the highest atom economy. You should be able to see that's B straight away, and not waste time. But if you have to work out atom economies for each one, atom economy is useful reactant, so in this case ethanol, divided by the MR of all the reactants. You get for A, 51.1%. B, because it's no side products, no waste products, it's going to be 100%. C, 36.2%, and that's really, you could have spotted that's going to be really high because it's got bromine in the waste products, and that's quite a large atom compared to the ethanol. And then D, 42%, somewhere around there for that, for the it's hydrolysis. So we've got our 4 atom economies, and C was the lowest. So the answer to 7 is C. 8, breakdown of ozone is catalyzed by NO radicals. So it's telling us it's by NO radicals. So which equation and propagation step for this reaction? Is it A, B, C, or D? So A and B are the only ones with NO catalyzing them. And A is forming ozone. So it's probably not that breaking it down. So it's B. 9, which compound could have produced this IR spectrum? So with this, we've got 3 peaks after 1500. So I always look, what do I have after 1500? And identify those peaks, and that'll help me to identify what we have. So we've got this peak at about 2,300 centimeters cubed to the -1. 2,800. A nice broad one at 3,300. So definitely an OH. I suppose it could be an NH. Definitely a CH. And then here, this is the big clue one that we looked at 2,300. Can only be the C triple N. So we've got nitrile. So we're just looking for which one of these has a nitrile, and the answer to that is B. So 9B. I think mistakes could have made there. You just ignore that peak and don't try and identify it. If you do identify all 3 peaks, it's pretty simple. 10. Benzene reacts with an organic reagent present for halogen carrier to form phenyl ethanone. Which organic reagent is required? So with a halogen carrier, we're looking for something else with a halogen so that it can take away that halogen for us. And so the only one there is C, and it's the acyl chloride. So chlorine goes to the halogen carrier, so AlCl3, gives you your CH3 to add on. So 10 is C. How many straight chain structural isomers of C7H15Cl contain a chiral carbon atom? So if I draw out that C7H5Cl, and I'm going to move my chlorine round and see if I can get a chiral carbon. So this won't be. If it's on 1, because we've got 2 hydrogens there, so 2 are the same, won't be a chiral carbon, be able to superimpose. So let's move the chlorine to this carbon, so 2-chloroheptane. And we've got chlorine, it's got hydrogen there, CH3 there, and then long propyl chain there, no, pentyl chain. So that's 1, if we put the chlorine there. If we go here, ClH, this again, this time butyl chain that way, ethyl chain that way, ClH, 4 different groups around there. So that is, so we're up to 2. If I put it here and here, I've got then a propyl chain that way, oh, and a propyl chain that way. So that can't be. And then we're just making it, put the chlorine there, it's the same as 3 chloro. So there are 2 that we can do. So 11 is B. Next up, 12 mass spectrum shows shown on there, which is responsible for the peak with the greatest intensity. Have a look at where that peak is with greatest intensity. We should see it's at 43. A has the MR, if you add them up, of 44, so we can't do that. B has the MR of 42, so it can't be that. C has the MR of 43, so it could be that. D also has the MR of 43. That's CH3CO. So how do we tell whether it's C or D? And to do that, let's look at their structures. So we've got CH3 to CH ion, and we've got CH3 CO ion. Both have the same MR. And we're going to look at the original structure and think which one of them can fit in to the original structure. Because these are fragments of that structure. They've been broken off it. They've not been, it's not like the atoms have broken down and reformed into these. These are actual fragments of this structure. And hopefully we can see if we just cut there, we have that CH3 to CH. So we can form that one. This one, if we cut at the oxygen and look at the oxygen, so maybe cut off that hydrogen, we can get CH2O, but not CO. So this one can't be done at all from that. So the answer's C. 13. Which statements support the delocalized model of benzene? It's often easier just to draw benzene out here. So in this, all carbon-carbon bonds have the same length. Yes, that is true. They do all have the same length. The enthalpy change of hydrogenation of benzene is less exothermic than expected. Definitely, it's a bit more stable than we'd expect it to be. And 3, bromine reacts with benzene less readily than with cyclohexene. Definitely, this does not react with benzene. Cyclohexene decolorizes bromine, whereas benzene does not. So we've got all 3. So A, 13A. And this is often actually put in a much longer question. You might get 3 or 4 marks for that. When they put it into multiple choice, you only get 1. 14. Solid organic compound can be purified by recrystallization. So recrystallization, we're going to put our mixture in. So I've got A and B there. Heat it up so they all dissolve. Let it cool. And then hopefully A all forms together, B stays dissolved, and we can then filter out and take our A. So organic compound is more soluble in hot solvent. Yeah, we heated it up. So 1 is true. Heated up at the beginning to get it dissolved. The hot solution is cooled before the purified organic compound is collected. Yeah, we need it to do that in order to get it there. And then 3, the melting point of the purified organic compound is lower than the input pure compound. I think that makes, it could be any, it could be above, it could be below. No, purified organic compound is lower than the impure compound. No, it could be any. So that's not true. So it's 1 or 2. So that's B. Because B could have, B stays dissolved in, it could have a melting point of 60 degrees Celsius. The melting point doesn't determine how soluble it is in the solution. It could be 120, it could be 150. Yeah. Unless I'm missing something there. The answer to that one was B. And then 15, I'm going to check that actually, because that seemed like word 1. Yeah, 14 is B. And then 15, which of the following could react with the compound below to form a carbon-carbon bond? Ooh, carbon-carbon bonds. So CH3Cl and AlCl3. They are nice. That's going to latch onto our benzene ring and put a Cl on the benzene ring, isn't it? With CH3Cl and a halogen carrier. So yeah, we've got there, which will react. Oh, it's CH3Cl. Ah, it's not. Sorry, I read that Cl2. So that's CH3 being added onto a benzene ring. I was about to say there, that doesn't form a carbon-carbon bond, but it does. We've got a carbon there, so So we've formed a carbon-carbon bond. So that is correct. KCN in ethanol. Oh, brilliant. Yeah, that's going to go nice and easily up onto our carboxylic. To add a CN on. And that's a carbon-carbon bond. So yeah, that one is. And then CH3OH and H2SO4. Go back. That is going to form an ester. Which isn't a carbon-carbon bond, because we've got an oxygen in the middle. Oh, that's tricky. Yeah, so the ester one won't, because we'll have an oxygen in the centre. So 1 and 2 are, so that's B. And that is a long video on the 15 multiple choice questions.